Hello everyone. Today we are going to discuss about serializability. Serializability, as we understood in the earlier lecture, is one of the concurrency control techniques. As we know, a schedule is an order of multiple transactions executing in concurrent environment. And we have seen that a schedule can be a serial schedule or a non-serial schedule. By serial schedule, I mean the transactions execute one after the other. It is a consistent nature. There is no interference, so I can assure data consistency in a serial schedule. What you see here is transactions of T1 have completed and then only T2 starts. A serial schedule, one particular transaction completes, then the second one begins. When that completes, the third one begins. It goes like this. Whereas in a non-serial, concurrent or simultaneous or parallel schedule, the transactions are interleaved. So interleaved in the sense they may be overlapping. So T1 has 4 transactions, reading and writing of database object A, then reading of database object A and writing of B. What has happened? The 2 actions are performed. In between it was T2. Okay, maybe writing took longer time. T2 has taken over and it was read and write of T2. Then again T1 continues, then T2 continues. So what we see is there is interleaved execution, or otherwise overlapping transactions, due to which there may be inconsistency of the data, because we have seen that concurrent executions may lead to conflicts. What is the serializability? Serializability is the property that ensures that the concurrent execution of a set of transactions produces the same result as if these transactions were executed one after the other without any overlapping. That is serial. So, if there are going to be conflicting actions, by rearranging those non-conflicting actions, I can see to that this particular non-conflicting schedule can be, or non-serialized schedule can be serialized. So serializability ensures that even concurrent execution that can result in the same result or same output as the serial transactions. Why serializability is important? We know that we have, due to performance optimization, we go for concurrent execution, simultaneous execution. But this can introduce several data inconsistency problems. Now, to ensure that we'll overcome that, serializability is used. So, serializability ensures that even when the transactions are executed concurrently, the database remains consistent, producing the result that is equivalent to the serial execution of these transactions. Because we have understood that serial transaction ensures consistency, whereas non-serial, it may be consistent or inconsistent. But even in case of that, I can ensure consistency by checking for conflict serializability or view serializability. What is conflict serializability? Now, conflict serializability determines if a concurrent execution of several transactions is equivalent to some serial execution of those transactions. You have a set of transactions. So, conflict serializability says that these concurrent execution can be modified, or a little bit can give you another schedule which can give you the same action of some serial execution. Okay. So, when a schedule is converted into a serial schedule by swapping non-conflicting operation, it is called as conflict serializability. So, we say that a schedule, yes, is conflict serializable if it is conflict equivalent to a serial schedule. Now, after all, what is this conflict? What do we mean by conflicts? See, conflict, the two operations are said to be in conflict when these three conditions hold. That is, they belong to a different transaction. That is, if one of the action is from T1, the other action should be from T2. Otherwise, general Ti and Tj. They should be accessing the same data item. That is, both of them should be accessing the data item X. Okay, and at least one of them should be right. Remember, when you have only read, everybody is trying to read the data, no conflict at all. But one is reading and one is writing, or one is writing, other is trying to read, there is going to be conflict. So say again, we can talk about railway ticket reservation. If both the transactions C1 and T2 is trying to see the available seats for Nizamuddin Express from Hyderabad to Delhi, there is no problem at all. Both of them are just trying to see. Or one is trying to see the seats available to Delhi, the other is trying to see the seats available to Bangalore by some other train. There is no problem at all. One is updating the result or number of available seats for Bangalore, and other is reading the available seats onto Delhi, no problem at all. So see, a combination of read on the same object, or read on different objects, or read write, or write or write read on the different object are all non-conflicting. But when you are performing the actions on the same object and one of them is right, see, we are trying to read A by through transaction T1 and write A through T2, then it is conflicting. Or you are writing A and reading A by T2, conflicting. Or T1 and T2 both are trying to update A value, it is conflicting, because the value updated by one may result in a different way in another transaction. Now, how do we test whether a given schedule is conflict serializable or not? Or testing for serializability is through a special graph called as precedency graph. Now, how does this precedency graph work? A precedency graph or a serialization graph is used commonly to test serializability of a schedule. It is a directed graph G of vertices, set of vertices and edges, where vertices V is all the transactions in the given schedule, T1, T2, T3, and the set of edges are the directed edges is an arc from Ti to Tj if two transactions conflict, that is for a conflicting pair. For example, here read of A and write of A on the same object. When you are performing read and write operation, we have told that it is conflicting pair, and Ti is accessed the data item before Tj. That means T1 to T2 there will be an edge. Let's try to see this particular thing through an example and then we will come back to it. So here, when I take this transactions T1, T2 and T3, see, one second, here we go. Okay, the vertices here are T1, T2 and T3, because there are three transactions in this schedule S. Now, how do we draw these edges? Let's see this particular first transaction action called as read of A. On data object A, we are performing a read operation, and I should look for a conflicting action in the other two transactions. For a read operation, conflicting action would be write. So write on A is treated as the conflicting operation. So when I say this, now here we see that write on A is present over here. That means I draw an edge from T1 to T2. Similarly, the next action is read of B, and as we know, read of B, the conflicting action would be write of B, and T3 to T2 I draw an edge. 3 to T2 I draw an edge. Next action is write of A. For write of A, there can be two conflicting actions. It can be read of A or write of A. Look for that in the set of transactions. For write of A, in T2, I have got write of A. So T1 to T2. Anyway, that is already there. I need not write it again. And in T3, let me see after this write of A, there is read of A. That means T1 to T3 also I draw an edge. Next, I have got write of B. There is no action on B here. I have got read of A. T3 to T2 already there is an edge. Then write of A. This is the last action. So this is what is your precedence graph. Okay, drawing the precedence graph is clear to us. We have seen that here also. We do see that similar graph here. T1 to T2, T1 to T3 and T3 to T2, there are edges. Now, what is the conclusion based on the precedency graph? The conclusion says, if there is a cycle or a loop in the precedence graph, it is not conflict serializable. Whereas, if there are no loops, then it is conflict serializable. So, if the precedence graph is acyclic, the schedule is conflict serializable. That means there is a possibility of converting it into a serializable schedule by interchanging or by swapping the non-conflicting actions. So this is what it says. If there is no cycle in the precedence graph, it means we can construct a serial schedule S dot which is conflict equivalent to the schedule S. So here what I see is, if I non-conflicting, when I say non-conflicting actions, look at this. If I have got read and write here, look at this here, read on A and read on B, two different objects. That is why they are known as non-conflicting actions. I can just bring it down and this can be taken up. That is what we see in the converted thing. Read of A has been just swapped. Read of A and read of B have been swapped. Coming to here, this action where we have write of B and read of A on two different objects. So that also can be swapped, and we see here that it is swapped. So write has been brought before. So in this particular schedule, which has the same actions as your previous schedule, but what we see is the non-conflicting actions are swapped, because of which T1, T3 and T2 have become serial. That is, only after completion of T1, T2 starts. On completion of T2, T3 is starting. So there is no interleaving or overlapping, and we see that this can be executed as a serial schedule. So that is what, because there is no cycle, which means that we can construct a serial schedule by swapping non-conflicting action, creating a conflict equivalent schedule. So precedence graph can tell you whether a particular given transaction becomes conflict serializable or not. So we'll try to see this example on two things. Let me just take up the pen again. Okay. So how many vertices are there here? T1 and T2. Let's look for the arc, read and read on A. And read operations are not conflicting, they are non-conflicting. At least one of them should be right. Okay, coming to this, read on A, but there is write on A. Read on A and write on A, there is an edge from T2 to T1. Let's go with the next action. We have got write on A and read on B, non-conflicting. Read operation, There is no operation here. In the same transaction, if there are operations, they need not or they don't affect. So here also we see that there is no cycle. Hence, this schedule S is conflict serializable. It's called as conflict serializable. Okay, let's take up another example. So this is what we have seen, that it is conflict serializable, and taking them because there is no cycle and changing it, I just have to see to that. And again, actually speaking, when I talk about they are serializable, if I have to identify which transaction or what should be the order of transaction, I have a method wherein I see the in degrees of the vertices. So here if I see the vertex for which the in degree is 0 becomes the first vertex or the first transaction to complete. So in this T1 and T2, if I see the vertex T2 has in degree 0, that is why T2 comes before T1. The order would be T2 followed by T1. That is why we convert it by using the non-conflicting schedules, by swapping the non-conflicting schedules. Here I can swap this one up, bring this down. So in that same order, one by one, step by step, I can see to that T2 executes before. Even in the previous one, if you see, when I talk about this particular thing, in order to convert it, the order of execution would be, if you see here, I have got T1 whose in degrees are 0. That is why transaction T1 will be executed first. Now along with this vertex, when I remove, I also remove these two edges. Now I have got T3 and T2, in which the T3 has got in degree as 0. So next one in order would be T3 and followed by T2, the left out. That is why you see here T1 has completed first, followed by T3, then T2. Here we made a mistake. Okay, followed by T3, then T2. So the order can be decided by using your in degree concept. Okay, let us quickly try to see the serializability test here on another two examples. Here when we go for it, okay, here for the first example, I have got T1, T2 and T3. RA, read and write here. So there is a conflict from T1 to T2. Then I take read of B. There is no read operation, so there is no problem at all. The next action is write of A. The conflict for that is write and read operation on that. I see that T1. So T2 to T1, there is an edge. T2 to T1, there is an edge. Then when I come to this T1 to T3, there is an edge. Now if you watch this particular graph, precedence graph, we see that there is a cycle. I start from T1, I can reach T2, or I start from T2, I can reach T1. There is a cycle of length 2. A cycle indicates that this is non-conflict serializable, or I say that it is not conflict serializable. So this schedule cannot be converted into a serial schedule. Okay. Similarly, let us try to see this T1 and T2. Another example, T1 and T2. When I say read and read operation, there is no conflict. Read and read, so nothing here. Read on A, and all these are either read or it is on a different object, so no conflict. Look at the second one, read of A. Read of A, there is write of A here. So T2 to T1, I draw an edge. Okay. Then read of B, the next one. Read of B, I have got write of B. So again T2 to T1, no need. Then I have got write of A. Here I don't have anything on that. I have got write of B. There is read of B. There is write of B, which is a conflicting pair. So again I have from T1 to T2. So what I see is a cycle. That means it is not a conflict serializable schedule. testing for serializability, we'll just try to see this example. So in the examples here, whatever we discussed earlier, there is, we have drawn it there, but once again I'm just going to tell you through this. We see that there is a cycle here between T1 and T2, says that it is not a conflict serializable schedule. Similarly here also, this is not a conflict serializable schedule because of existence of a cycle. This is another example where when we talk about a cycle again, if you see here, we see that from T1 you start, go to T3, then T2, then T1. That means there is a cycle in this particular example also. Whenever there is a cycle, we say that it is not a conflict serializable schedule. Thank you so much. See you all in the next session.